What we find in chemistry is that a lot of crystals, ionic crystals, actually have water molecules inside them. And this is called water of crystallization, because it's water inside the crystals. The water molecules have got a relationship with actually the cation of the ionic compound. It's usually found with ionic compounds with a cation is what we call a transition metal. So it's from that middle section of the periodic table. And that's because of their high density, therefore high charge density, can attract the slightly negative part of the oxygen of a water molecule, making a, if you want to know, it's like a sort of dative bond. You don't learn about until next year. So when we see a formula like this, CuSO4 5H2O, this is a blue crystal, by the way, it means that for every copper sulfate, so every 1 copper, 2 plus every sulfate, 2 minus, there's 5 H2O molecules in that as well. So it's just known that that's part of the formula. So as before when we were working out molar masses and stuff, we include the 5 waters in its molar mass. Now if I was to heat that, then it becomes CuSO4, which is actually a white crystal. It's got no colour at all. So the 5 waters can be evaporated away without it actually destroying the crystal. It does change the physical properties of the crystal though. It's different. It's lighter for a start. It's lost those 5 water molecules for every CuSO4, so it's a lot lighter. But you'll notice it's also got a different formula, and also in this case, which is not always the case, in this case it goes from being blue to being colourless. So sometimes we can see the difference between the two types of crystals. The one you're going to work with today is this exact one, but the one I'm going to use in the example goes from being a colourless crystal, which is kind of opaque, to an opaque crystal. So there's no visible change. So what we have to do is use mass. We weigh it at the start, we heat it, we weigh it again. We heat it, we weigh it again. If the weight the second and third time hasn't changed, we know we've finished. If it has changed, we heat it again, weigh it again, heat it again, weigh it again, until the weight doesn't change. Then I know that I've driven off all the water. So what you'll end up with are things like this. And I'm reading from our book, Beginning Chemistry, page 76. I'm just going to do it a little bit different the way they have. They've said that 4.96 grams of hydrated sodium thiosulfate, that's this thing here, was dehydrated, so heated until all the water was gone, dehydrated, and formed 3.16 grams of the anhydrous, from here, anhydrous means no water of crystallization, anhydrous salt. So I'm going to put those numbers in because I know them. We're going to try and find X, how many water molecules have been driven off, okay, to find its hydrated formula. So I know the mass of a hydrated salt. Even though I don't know how many waters, that's irrelevant. I know how much it weighs. So it's 4.96 grams. I know that at the end, after I've driven off as much water as I can, I ended up with 3.16 grams. Now, knowing a thing called the conservation of mass, because this is just a chemical reaction or a physical change, actually more than anything, it's not going to do anything clever. So conservation of mass applies, which means this number plus this number has to equal this number. It's just simple math. So I can find out how much water was released. So 4.96, my quick math says 4.96 minus 3.16 will give us this value, which I'm pretty sure is 1.8 grams. Okay. Now, we don't actually need any of the rest of that. Alright, we actually don't. Not hugely anyway. We're going to need this one, sorry. We're not going to need any of this. Okay, because we don't know these numbers because of this. It's got an unknown. This bit's irrelevant to this. We can't do it. Alright? What is important is the ratio between these two. Just like when you did percentage composition. We're trying to find the mole ratio between these two. So how many of these for every one of these? So what I do is I then work out my molar mass of these two things. Ignore the x because that's the quantity. What I'm looking at is only the formula. And we now know that, because we've used water so many times, we should know that water is how many grams per mole? 18. Fantastic. So I'm going to put 18.0 grams per mole there, because I know that one. This one I'm going to have to work out. Now luckily we've got it in front of us in our books, so I'll just quickly jump to that and check. And it's 158 grams per mole when it's rounded to 3 Fs. Okay, so if you do want to go through the slow one of that, 2 times 23, 2 times 32.1, and 3 times 16 adds up to 158. Right, so now I've got, in each column I've got only one unknown, so I can solve. So if I go 3.16 divided by 158, I end up with approximately 0.02. Okay, so approximately equal to 0.02. Don't think it's exactly that. And if I go 1.8 divided by 18, then I should get 0.1 for that exactly. Okay. Now, just like when we did percentage composition to work out empirical formula, we divide by the lower of those two numbers to get a 1 to something ratio. Okay? So if I look at this, 0.02 is smaller than 0.1, so I divide both sides by that. And on my calculator, although the first one's going to count for 1 because that's the whole intention, I'm going to end up with 1 to 5. What that means is that the x is going to be a 5. That x is 5 on both sides. So therefore the formula for this one is also going to have 5 waters in it, so it's all pentahydrate. So the overall formula, given this number here, will be that. Now if I get something like 4.7 or 5.2, they're close enough. You can't have fractions because these numbers have to be whole. So make a bit of a judgment call in your experiment whether you should round it up or round it down, what seems most likely. You may have to do some research to check what it should be, to hope like heck that you're close to it. If they're not pretty close to exactly those numbers, so they're not within say 4.9 and 5.1, then maybe you didn't heat it for long enough. That's the most likely thing. Or some of the salt is actually burnt while you've been heating it on the flame. So that can happen as well. So there's a couple of reasons why you don't get the right answer. This used to be an internal assessment, but because there's so many ways you can make errors, they've taken it out now. It's just something we will give you the data in an assessment, and you have to work out the hydrated salt formula. Okay? So just to go through it again very quickly, I write an equation with the x's in it. I write down what I know in terms of mass, which means I normally have to calculate the mass of the water. I calculate the molar mass for these two, for the anhydrous salt and the water, and I work out the moles. I then divide by the smaller value, which will always be the anhydrous salt value, to give me a ratio of 1 to something. I round that ratio off, so if it's 4.7, I'd say it's 1 to 5. Okay? So I round that value off so that I can get a value for x.